All right. Well, good morning or good afternoon if you're in first or fifth block. Today, what we're going to be learning about, we are going to start our section on graphing rational functions. So, this is 7.5, Graphing Rational Functions, day number 1. Today, what we're going to do, our objectives, our goals, should be able to use technology to graph rational functions and to find precise values for the x-intercepts. Should also be able to state the behavior of a rational function when looking at the graph, and should be able to identify transformations of rational functions. Okay, so what we're going to do first off is we're going to work on sketching graphs of rational functions. We're going to do so using a graphing calculator. When we do this, what I want you to do is I want you to find all of the x and y intercepts and then go ahead and sketch a graph. So in your graphing calculator, what you need to be careful of when you're typing in something such as 3 over x minus 2, the x minus 2 and really numerator and denominator both should really go in parentheses unless your calculator can type it in as a fraction. If you can't type it in as a fraction, feel free to do that. But for those of us who cannot do that, you need to type it in as, for example, the first one, if you're going to type in 3 over x minus 2 in a graphing calculator, the way you have to do that is you have to type it in as this. You have to type it in as 3 divided by parentheses x minus 2. So just know that you might need to use parentheses if you cannot type it in as fractions. Okay, so graphing that first one, here is basically a graph of what that will look like. So again, what I did was went in and put my first equation in, 3 over x minus 2. I also have the other ones in here just so that later on we don't have to take as much time looking at those. But the only one that is graphing right now is this 3 over x minus 2. So the graph, when you go to a standard viewing window, here is what that looks like. Now, couple things I want us to look for, one of which is this y-intercept. The way you find a y-intercept, remember, that's where your x value is 0. So hit trace, and most of the time it will auto set to that y-intercept. So when you hit trace, it'll tell you that x is 0. It'll tell you that y is equal to negative 3 over 2, which as a decimal, negative 3 over 2 is negative 1.5. So that's going to be one of the things we look for, is that our y-intercept here is going to be at 0 and negative 1.5. Now, as far as x-intercepts, notice that while the graph approaches 0, it never actually reaches 0. In fact, it will never reach 0. This is an example of a horizontal asymptote. So, meaning that the graph is going to approach 0 as it goes towards infinity and negative infinity, but it will never actually reach 0. So, for x-intercepts, this one actually will have none. Okay, so giving a rough sketch of what the graph looked like. We already said that it had a horizontal asymptote at y equals 0, so on the x-axis at a horizontal asymptote. The way I'm going to graph that in, and this is really more to help you graph the rational function than it is a part of the function, but I'm going to go ahead and draw in that asymptote. Okay, it looks like we also have a vertical asymptote at y equals 2, meaning if I were to kind of draw a dotted line down through 2, it looks like we've got a vertical asymptote at x equals 2. So once again, this is not an actual part of the graph. You'll notice that, in fact, on the graphing calculator, it did not even show these. But just to help us graph in just a little bit, I'm going to go ahead and draw those in. Okay, now for the graph itself, we said y-intercept at 0 and negative 1.5. And then to draw the rest of our graph in, basically what we were looking to do there, we had a curve kind of coming down, and I didn't do a good job of connecting it. Hopefully you'll do a little better. Let's make my point a little larger. So there's one half of my graph. The other half started up here and kind of came down, and here would be the second half. What a rational function almost looks like when you graph it, it's almost like it has an exponential function in a couple of different places. It's kind of what it looks like in a way. But there would be our first graph. Okay, so second graph was this. We're going to now graph this function x minus 1 over x squared minus 3x plus 2. So I've already got this one ready to go. All we need to do on graphing calculator is turn off the equal sign here to say we want to turn that line off. We'll go down here and turn the equal sign on there to say we do want to graph that one. And then what I'm going to do, shouldn't have to because it was already in standard viewing window, but I'm still going to go ahead and do zoom 6 to go back to standard viewing window. And here's a graph of what that one looks like. So once again, it looks almost like it's going to cross. It almost looks like it's going to go through at 0 when it ends up not. So it does look like our asymptotes are going to be about the same though. It looks like you're going to have one through x equals 0 or not x equals 0, through y equals 0, and another one here through x equals 2. The only thing that looks like it's going to really change in this graph is our y-intercept, so let's go ahead and find that. Let's press trace. And once again, trace will oftentimes auto set to x equals 0 with a y value of -1/2. So we'll put that as a decimal. For this one, let's see, y-intercept was at 0 and -1/2, so -0.5. We did not have any x-intercepts once again. And then let's go ahead and draw in our asymptotes. So we had an asymptote here running through y equals 0. Had another asymptote running through x equals 2. And then the one point that I am going to look for in terms of graphing for accuracy is the y-intercept, since there were no x-intercepts. So at 0, -1/2 right here. And then once again, here is your graph. All right. So last graph here, we've got f of x equals x plus 2 and x squared plus 2x. Let's see what we get there. So again, y equals, type that in if you have not already. For me, since I've already got it in there, I just need to tell my graphing calculator to turn that on by pressing enter for the equal sign. And when I graph that, here is what that one looks like. So this one looks quite a bit different. In fact, it almost looks like it kind of stops at some point. Now, let's hit trace. And for 0, notice that it says that y is undefined, meaning that for this problem in particular, you essentially do not have a y-intercept. Now, x-intercepts, once again, it looks like we're not going to have any there. So really for points, you're not going to have a lot that you can graph. But you should be able to still draw in your two asymptotes to kind of help you with graphing the rest of it. So one asymptote is still the same, a lot of y equals 0 asymptotes. And then our other asymptote, it looks like, was running through, this time, the y-axis as well, through x equals 0. So here would be that asymptote. And then it looks like our graph, again, looks something sort of like this. All right. So x and y intercepts, I guess we've talked about them, we haven't written it down yet. Remember, x intercepts, there were none, and then same with y intercepts, there were none there. All right. So now for this next two examples, it says based on each of the following graphs, state the end behavior for each rational function. Remember, end behavior only concerns itself with the ends of the graph. So as you look at these, the only things you should be looking at would be like this piece right here and this piece right here of number 4. Or on number 5 would be this piece right here and this piece right here. Now notice on number 4, there's a lot going on between those two end behaviors. Same with number 5, but that's the thing about end behavior. End behavior is just what's on the ends of your function. So for my end behavior for number 4, and remember we are using limit notation. So we're saying the limit as x approaches, let's do -infinity first. As we get closer and closer to -infinity, our function f of x is getting closer and closer to 0. So going to the right now, the limit as x approaches +infinity, f of x in that direction is also approaching 0. So we're approaching a value of the number 0. Okay, on this graph, and this is kind of interesting, our limit as x approaches -infinity, as we go to the left, our function f of x, it looks like is actually going down, and it looks like it's going to keep going down, meaning that we're going all the way down to -infinity. And so then limit as x approaches +infinity, our function f of x, this time, if you notice, is going up towards +infinity. So you'll notice up here in our top, that is going to positive infinity instead. So looking at a graph, that's kind of how you tell the end behavior. Is you just look at the ends, what value is it approaching? Is it approaching some number, or is it going towards infinity or negative infinity? Okay, so next thing we're going to talk about, and really last concept for today, is going to be all about transformations. Now, the parent function for a rational expression or a rational equation is this right here. F of x equals 1 over x. So, when we look for transformations, what you sometimes want to try to do is get 1 over x by itself. For example, like on number 6 here, one way you can rewrite 2 over x is to say 2 multiplied by 1 over x, which sometimes helps you see what the transformation is going to be more clearly. 1 over x is just the parent function. The 2, which is a number out in front, is being multiplied. Which, remember, whenever you're multiplying a parent function by some number which is in front of it, that's either a vertical stretch or a vertical compression. For this one, because 2 is bigger than 1, we would say that this is Vs, a vertical stretch, by 2. Okay. Now, for number 7, we can't necessarily just move this negative 2 out. We can't move the negative 2 out to the right. It's stuck inside the parent function, and if it helps, you can put it in parentheses. That would be how you'd have to type it in your calculator. So if it's inside the parent function, remember that's your horizontal movement. In this case, if it's negative 2, you have to think opposite. This is actually moving to the right by 2. All right, so number 8. Here we've got a negative 2 outside of the parent function. So remember, outside the function is going to be a vertical shift. If it's negative 2, that's going to be what tells you that it needs to go down by 2. All right. Got a few more for us to look at, and then I'll give you a chance to try some on your own here. Okay, so in number 9, you can, if you're multiplying, still move the 2 out in front. Notice it's 1 over 2x. The way you have to do it, though, notice that 2 is in the denominator, so you need to leave 2 in the denominator. You can put a 1 up in the numerator, and then your parent function, remember, is still 1 over x. And if you need to, you can always check yourself. Working backwards, 1 multiplied by 1 is 1. 2 multiplied by x is 2x. So when you pull out numbers that are being multiplied, it needs to stay in either the numerator or denominator. Now in this case, 1/2 is a number being multiplied in front of the parent function, so that's going to be either vertical stretch or vertical compression. In this case, because it's smaller than 1, we are going to say that it's a vertical compression. All right, this next one has a lot going on here, so we're going to take it kind of piece by piece. The negative that's out in front does the same thing as it always has. That is a reflection over the x-axis. So there's your first transformation. Now the 3 that's in the numerator, if you were to pull it out in front of my parent function, would be just a 3, meaning that you have a vertical stretch by 3. Essentially, if the number is in the numerator of the fraction, you'll have a vertical stretch. If you have a number being multiplied in the denominator of the fraction, it's a vertical compression. So if you'd like to add that into your notes, once again, that is any number in the numerator being multiplied is a vertical stretch. Any number being multiplied in the denominator is a vertical compression. Now the negative 1, still need to talk about that. That's going to be what tells you that this one also moves down by 1. All right. So, tell you what, at this point, I'm going to let you go ahead and continue working. So, if you would like to work ahead, 11, 12, 13, 14, press pause on the video now and work through those. I will go ahead and work through them in just a little bit. All right, so on number 11, we just got done talking about this. If you have a number in the numerator, remember, if you were to pull that out in front, is a whole number larger than 1. So we said any number being multiplied in the numerator is a vertical stretch. So this one is a vertical stretch by 4. Denominator, you've got an x plus 5, which again, if it helps, put parentheses around it. That is going to be a horizontal transformation. So this is going to be one that moves to the left by 5. Remember, inside of parentheses is opposite of what you would normally think. Okay, now this next one is a tricky one, and I really hope that you are checking your work. What you need to do on number 12, you need to rewrite this fraction factored. So it hasn't been an issue up until now. What you need to do, if it's not already, you need to factor. In other words, factor a 2, a GCF from your denominator. There's actually going to be a couple of things going on here. The first, notice that you are multiplying by a number in the denominator. That's going to be what tells you that this is a vertical compression by, in this case, 1 over 2. Now, again, the reason you need to factor is that also affects your transformation. Now, your horizontal transformation, you are going to be going to the left by 2. If you didn't factor out a 2, you can still get that there's a left by 2 transformation by setting 2x plus 4 equal to 0 and solving for x. When you solve for x, in that case, you get negative 2. That would have given you a hint that you're going left by 2. But probably the easiest way is to just factor out that number. Okay, and then this last part, the negative 3, is what's going to tell you that you are also going down by 3. All right. Next one here, number 13. Looks like we've got a negative in front, which is going to tell you that you reflect over the x-axis. It also has a 7 being added outside of the parent function. Outside tells you up, down, so this one would be telling you that you go up by 7 as well. All right, this last one is a hard one. Okay, so once again, first thing you should do is go ahead and factor the denominator. Now, it sounds weird because there is no common factor, and so in that case, we really can't do anything. What we can do, and it's kind of a tricky thing that we can do, well, let's go ahead and try to factor as best we can. So, negative 2 over, in this case, if you factor out a 3, in other words, we're going to take both of these terms, both the 3x and the 5, and divide by 3. Then, 3x divided by 3 is just x. 5 divided by 3 is 5/3. Or as a fraction, 1.6 repeating. Don't forget you still have the minus 4 there. Okay, now here's what I'm going to do. I'm going to go ahead and pull this 2/3 to the front of my fraction. So, similar to what we've done in the past, I'm going to pull this 2/3 to the front of the fraction. So what that's basically going to look like, you'd say negative, pull the 2/3 out in front. Here is my parent function, 1 over x plus 5/3, and then minus 4. So, it's a very sneaky one, because if you were originally thinking that it had both a vertical stretch and compression, that's not going to be the case. One will take precedent. Because denominator is larger, that would tell you that denominator takes precedent, meaning that you'd have a vertical compression, but now it's a little bit easier to see. 2/3 is going to be something that is smaller than 1, so you're going to have a vertical compression by 2/3. You also notice have a negative in front, so another transformation you're going to have is that this is going to also reflect. So you're reflecting over the x-axis. You do need to be specific, so if you have not been saying over the x-axis, you need to start doing so. There are multiple reflections you can have, so please be sure you are saying which axis you reflect over. Okay, now, inside of my parent function, it looks like we had a plus 5/3. Remember, think opposite, so that's left by 5/3. And then notice that outside of the parent function, you had a negative 4, so you also have a transformation down by 4. That was a tough one, man. All right, so there is most of the notes. We've got one more to go, and we'll call it a day. Number 15. What it wants us to do is first graph f of x equals 1 over x, and then state the transformations for g of x, and use those transformations to graph it. Okay, so what we're going to look at here, if I have f of x equals 1 over x, which this one I don't have ready to go, so we're going to have to put that one in. I go ahead and turn off this third one, That way I'm not graphing any of those. And then line 4, I'm going to go ahead and now graph 1 over x. So I'm going to type that in just as division, save a little bit of time, 1 over x there. All right, so when I hit graph, here is what that looks like. So it looks like I've got a horizontal asymptote at y equals 0, and then a vertical asymptote at x equals 0. Looks very familiar to number 3 from the notes that we just did not too long ago. But let's go ahead and graph in those asymptotes first. So my first asymptote is right here through y equals 0. Second one was through x equals 0. All right, and then as far as transformations go, or not transformations, as far as graphing it goes, don't forget that we had a curve going down like so, and then another curve like so. Okay, now time to talk about transformations. It looks like g of x is going to be moving to the right by 2, and it looks like it's also going to be moving up by 3. So what I would do, I would pick kind of this central point of 0, 0, where it looks like both my asymptotes cross through, and I would move this point, even though it's not a point on the graph, to the right 2, and then up 3. So my new kind of center of the graph is going to be right here. Now what that means is now you've got a horizontal asymptote running through y equals 3. In other words, the only thing that affects the horizontal asymptote is any up or down movement. So for this one, up 3. And then let's see, to the right by 2, so that's going to tell me that my vertical asymptote needs to run through that point. So that's going to be going through at x equals 2. And so then my new graph looks like is also going to shift up and to the right. So that would look something kind of like this as you graph it. And try your best to make sure that those graphs are sort of hugging the asymptotes in a way. Try to get them to come as close as possible without ever actually crossing. All right, guys, that is notes for this Tuesday. Please be sure you work on homework and check that on Schoology, and I will see you back on Wednesday. Also, do not forget a couple announcements, and I'll post these on Schoology as well for you, but do not forget that you do have a Unit 7 quiz on Friday. That is a full-length quiz, so that will probably be a front and back quiz, not like a half-sheet quiz that we're used to on Fridays. And so that'll be pretty much all we do on Friday. And then I'm pushing Unit 7 test back by 1 day, and this will be the last time it gets pushed back. So Unit 7 test we are going to do on Friday of next week. So Unit 7 quiz will be on Friday of this week, which the date there, let's see, is going to be the 26th. So this is 1/26 here for the quiz. The Friday for the Unit 7 test is going to be on February the 1st. All right, guys, I will see you back Wednesday. Have a good rest of your Tuesday.